In this class, in this lecture, we're going to learn that loads are complex instructions. So either I may have a load to use dependency, as I saw before, or in earlier classes, or I may have a definition to address computation latency. And what I'm going to do when I have to process a load, I will speculatively wake up the load for execution, assuming that I have a cache hit. And if there is a cache miss, then I'm going to stop the execution of that load because I'm going to have to wait for the data. So the load dependencies are a bottleneck in the execution of the program. Here is an example, just to illustrate the example that we're going to work. There will be a store. There will be some other instructions that will be executed. Then there is a load. And then I have some more instructions that are executed, and then I have a use of the value of that load. So this is not necessarily the problem of the load use dependence that we studied early in the course, but we still have there is an instruction that is depending on the value of that load. I would like to obtain that value as early as possible for this instruction that's depending on it. So this is a load dependence that I have there. The latency of the load is variable. I do not know how long it is going to take to get the value because I may have misses in different levels of the memory hierarchy. Therefore, the latency is variable. So if that is a cache miss, and depending on the level in which I get cache misses for that to fetch that value from, I'm going to have different latencies. So a load may conflict with a previous state as well. What does it mean? With a previous store. So what does it mean for a load to conflict with a previous store? If I have this store here storing to the same address as this load, and the store has not yet completed by the time that the load needs the value that it's loading from, then I have a load store conflict because the load is going to have to wait for that store before it can advance. So if those are the same addresses, I have a conflict. But the compiler does not know whether this conflict is happening because either the compiler has imprecise pointer analysis or it may be impossible to know whether that dependency exists at compilation time. So what should I do in that case? So one thing that I can do is to predict whether the load and the store are going to have conflicts to make a decision about how to proceed. So what can prevent a load from proceeding? So maybe I don't know the address that I should load from. So for example, in this load, I need the value of S3 in order to compute the address, but maybe the value of S3 has been computed by another instruction, and this value is not yet ready for me to compute the address. Or maybe I have an old value. So in the memory. So the store that is storing a value to memory, that's the value that I should be loading, has not completed yet. So the content of the memory location has not been updated yet. So what we can do a load speculation. So if I don't know the address, then I could speculate what's the address that I should be loading from. This is used for prefetching. So the idea of prefetching is that I guess where the subsequent loads will access memory, and I start accessing those locations before I actually know the address. If I have the old value case, that is, there is a previous store that's storing to the same memory location that this load is loading from, then what I can use is a memory dependence prediction. In a memory dependence prediction, what I'm going to do is to predict whether that load is actually loading from a store that has yet not completed, and I use that to speculate on the data flow between the stores and the subsequent loads. So let's look at an example so that we can see concretely why sometimes I may not know whether there is a dependence or not. So let's consider this program. Notice that I assigning the address of A sub I into PA at the top of the program. And then I have a conditional at the end of that block. And if I follow the path to the left, I am assigning the value of X plus Y into A sub I. If I follow the path to the right, I'm assigning the address of B sub I into PA before assign X plus X into B sub I. And then at the join point, I return the address of PA sub 0 plus 3. So this is the address computation. And what I did now in this slide is I will show you how I'm transforming that statement into intermediate language so that I can produce the assembly code for that block. So the intermediate code will be that I take the base of the array A and I add 4 times I to that base to compute the address of A sub I, and then I use that address to access memory. That's my intermediate code. If I make these assumptions here that A is in A0, B in A1, PA into 0, and so on, then I can replace that temporary code with RISC-V assembly. In this case, we are assuming RISC-V in this example. And the code the number of instructions that will be executed before instructions for the block on the left. The block on the right, I can do a similar transformation where first I get the temporary intermediate code that does the computation of B plus 4 sub I and puts into PA, and then I access the memory in PA. So this gives me this code. Now I have a optimization that I can do here because this computation of multiplying T1 by 4 and putting the result on T4 is redundant on the left path and is also redundant on the right path because it has been computed before. I already have the value of T4, so I can simply eliminate that computation and I end up with this code here. Now what happens is that this load that I have at the join point in the bottom may depend on the store on the left and may depend on the store on the right. So let's see what happens. If I follow the left path, what I have is that the address that I have in 0 to 5 and in 0 to 0 are the same address. We can just see that the computation of T0 and T5 here is the same. However, if I follow the path on the right, what I have is that the address 0 to 3 and the address 0 to 0 are not the same address. I can just look at the computation of T3 at the top of the right hand side block. So the load does not depend on the store. So that's why depending on the path that you follow, you may have a load that is current in flight. You may have a store that's current in flight that that will cause a dependence or not, depending on the path. So that's why you cannot know at compile time what that load can be speculated or not. So another question is where I keep the stored value. So when I'm executing a store, there is a possibility that I'm executing a store in a speculative path. So I had a branch, I did a branch prediction, and that branch prediction told me to go down a certain path, and in that path I have a store. So the store is being executed speculatively. So let's assume that the address for that store has been computed, and I have the value as well. So now let's consider whether the value has been computed, and where should we write the value that the store is writing to, and what would be the consequence of writing that value into the data cache. Remember that we are executing a speculative store that we don't know whether it's going to commit or not, because we may be in the wrong path after a branch. So this store may not commit. So I cannot store that value in the cache, of course, because if I store that value in the cache, I will be corrupting the cache. I'm going to be eliminating another value that's in the cache that I may need in the future. So what I need is a temporary place for the value that will be stored so that I can keep that value in this temporary place until I make a decision if the store is actually going to commit or not. So what I'm going to use for that is a store buffer. The store buffer is a circular queue for stores that have not yet committed. So what I do, this store buffer is required because the written value must be stored somewhere before the instruction commits. When I decode an instruction and I find out that that instruction is a store, I'm going to allocate an entry into that buffer for that instruction. And when that store commits, then I can remove the store buffer entry because now I can write the data into the data cache and I no longer need the store buffer entry. So let's consider what are the states of a store buffer entry. This illustration is just a general illustration of a buffer showing that this would be the store buffer. And what we are talking about is the state of a single entry in this buffer. So each one of the entries in this buffer will start at the available state. So in the beginning of the program, all entries are available because we have not decoded any store yet. So when we decode the instruction and we found out that it's a store instruction, then we're going to move into the allocated state. So we're going to allocate an entry. So the entry that have been chosen for that store, now we're going to go from the available state to the allocated state. Then when I do the address computation for that store, so I know the location memory where that store is going to write, I go into the AG state, that is the state where the address is known. And the data to be stored is still to be computed by another instruction. So when the value to be stored has been computed, then I go into the RE state where the result and the address are known at this state. And then when the store instruction reaches the top of the reorder buffer, that's when the store is going to commit. In this case, I go into the committed state, where I have commit the store, but the data has not yet been written to the data cache. So then when the data is written to the data cache, I can go back into the available state because I no longer need that entry into the store buffer. So those are the 5 states of the store buffer. So what happens with the store buffer on a branch misprediction now? So the situation that I have a sequence sorry, I have a sequence of instructions on the right. Those lines indicate some other instructions. So I have some instruction, then I have a store, then I have some instruction, I have a branch, and then I have stores that are in the speculative path of that branch. Let's say that the branch was predicted to not be taken, and those 2 stores that are below the branch are being executed in the speculative path of that branch. So when I have a branch, the entries that precede the mispredicted branch, so let's assume that I mispredict that branch and I start executing those stores after the misprediction. So the entries that precede the mispredict branch are in the commit state and must be written into the cache. But the entries that follow the mispredicted state, they have to become available. Because once I decide that the branch was mispredicted, I decide that these stores will never going to commit, and I do not need the values that may be stored in these entries. These entries can simply become available at that point. If I have an exception that's thrown by an instruction, I'll do a similar situation where the stores that are before the exception instruction must commit. And therefore, if they are still in flight, I'm going to wait until they commit. Remember that I'm going to keep executing all the instructions before the exception until the exception cause instruction hits the commit stage. I must write the commit entries to the cache before handling the exceptions. So let's talk about the load instructions now and talk about the load speculation. So The most restricted implementation that I can have load and store windows in a FIFO situation where I put the loads in the store in the same queue. So I have a queue that will contain all the loads and stores. So it's a single window for loads and stores. So the loads and stores are inserted into this window in program order, and the loads and stores are removed from this window also in program order, and I remove at most one of those instructions in each cycle. So let's talk about load bypassing now. What we have here is a pipeline, and let's say that I'm executing a load in this pipeline, and when I get to the execution unit, the load gets to the execution unit is when I compute the address where I'm loading from. So the load address is known at the end of the execution stage. At that point, I can take that address and I can do an associative search in all the entries in the star buffer. So the star buffer is a content addressable memory or a full associative cache where I can search all the entries in parallel and I can find whether there's any entry that matches the address of the load. So if all the store addresses are known and there is no match, so I know that there is no store that is pending that will have a conflict with this load, I can simply proceed with the execution of the load. The load can bypass all these stores and there will be no problem in executing this load. If at least one store address is not known, then I have to decide whether I should proceed with this load or not. In a conservative implementation, the load cannot proceed because there is a store that may conflict with this load. If there is a match to an uncommitted store, so the result for that store, the value for that store is known, then the load cannot access the cache. And what I look in this case, if there are multiple matches, I'm going to look for the last match in program order. So I look for the last match that entered the store buffer before this load has entered the store buffer. So I must store information to track program order as well. But remember, if I'm executing loads and stores in orders, they're gonna enter in order into the store buffer as well. So if I can identify the last match, the last load that matched the load, I can do load forwarding. Load forwarding means that I do not access the data cache, but I can take the value from the store buffer for that load, and that operation, that technique is called load forwarding. If the store does not commit, so I have done a forward to a load from a store, but the store was in the speculative path of a branch, and the store actually does not commit. If that happens, then I have to keep track of that situation because I'm going to have to reissue the load because the load actually got a value from the store that did not commit. So in an out of order architecture, I have the dynamic memory disambiguation problem. The issue is that loads are issued speculatively ahead of preceding stores in program order. The question is, how do I ensure that the data dependencies are not violated? And I have three approaches for that. One approach is the pessimistic approach. In the pessimistic approach, I am not going to proceed with any load that can violate the data dependence. So I wait until I'm certain that a load can proceed. This is just load forwarding and load bypassing. There is the optimistic approach. The optimistic approach, I assume that there will be no conflict. I'm very optimistic. So the load always proceeds speculatively, and I will need a recovery mechanism. And then there is the dependence prediction approach, where I'm going to use a predictor to decide if I should speculate the load or not. And the idea is that I'm going to try to have a few recoveries because recoveries are expensive. But there's another issue with the predictors. I also want the predictor to not prevent loads that do not conflict from proceeding. So I wanted my predictor to be as precise as possible. So let's say that I have a sequence of instructions. I have two stores followed by two loads, and I may have many instructions in between these instructions. And let's say that there is a true dependence between the store at instruction I2 and the load at instruction I3. So in the pessimistic approach, I do not issue the load into I3 and I4 until I know the result of the load in the store in I2. I need to at least know the address of that store before I issue. If these two are in the address computation state, then the I4 can proceed because I know that there is no dependency with the I4. In the optimistic approach, I issue the loads I3 and I4 as soon as possible. And when they start reach the commit stage, then I compare the address associatively with all the loads that I have in the load buffer entries, and then I'm gonna redo the loads that had a conflict. In this case, in this sequence, I do not need to reissue I4, assuming that I4 has no dependencies in this example, but I have to reissue the load in I3. In the predictive approach, if there is that true dependency, I do a dependence prediction. If I have correct prediction, then I'm gonna let the I4 load to proceed because my prediction is that there is no dependence for that load, but I'm gonna avoid reissuing the I3 load because the I3 load is gonna wait for the store. So in the predictive approach, I do the best possible thing. That is, I allow the loads that have no dependence to proceed, and I hold back the loads that are predicted to have dependence. So what's the motivation for being optimistic? The motivation for being optimistic is that memory dependencies are rare. So less than 10% of the loads depend on an earlier store. The motivation for the prediction is that the misprediction are expensive and predictors can reduce them. And the other thing with the prediction approach is that I prevent what the pessimistic approach does, that is to prevent loads that have no dependence from proceeding. So the question is, what strategy should we use for predicting which speculations are profitable? There's a simple strategy that I can use that I say that memory dependencies are not frequent. So I'll predict that all loads can be speculated. If a load L is misspeculated, all subsequent instances of L must wait. So what I do, when I first see a load for the first time, I assume that this load can be speculated. But if this load has a conflict, then I mark this load as having a conflict forever. And as long as this load is in the instruction cache, I do not speculate that load. So we need a bit to remember that. Where should this bit be stored? I already indicate a simple strategy is to associate a prediction bit P with the instruction cache. So I associate this bit with that load in the instruction cache. When the load instruction is brought into the cache, I assume that the load can be speculated. And if the load is speculated, then I assign 0 to that load, and that load will not going to be speculated as long as it is in the instruction cache. So this works very well for a load that's inside a loop. When the line is evicted from the instruction cache and reloaded sometime later, then that bit goes back to 1. This is a strategy that is used in the DEC Alpha 21264 processor. So what's the principle behind load speculation? There is this quote here that I like from Andreas Moschovos from the University of Toronto, a colleague and friend of mine. It says that static store load instruction pairs that cause most of the dynamic data misprediction are relatively few, and they exhibit temporal locality. So we can rely on the fact that if a store load instruction pair cause misprediction, that it will cause misprediction again in the future. So we can design predictors to take care of that. So if I have a dependence between a store and a load, this dependence will happen with the temporal locality. So what's the ideal load speculation? I'm going to avoid all mis-speculations, and I'm going to allow loads to execute as early as possible. So an ideal speculator will not only avoid the mis-speculation, avoid having to reissue loads, but also going to allow loads that have no dependence to move forward as soon as possible. There are two cases. One, loads that have no true dependencies, and the other are loads with a true dependence. So if the load has no true dependence, I should execute without delay. The load with a true dependence, I should execute as soon as the store that produces that data commits. So let's talk about the real predictor. The idea here is that I will dynamically identify store load pairs that are likely to be data dependent, and I will create a synchronization mechanism to the instances of these dependencies. And I will use this mechanism then to synchronize the store and the load. So the idea here is that I'm going to have use a predictor that will work very similar to a branch predictor, where I'm going to have a hash that will go into a table of saturating counters, and I'm going to have the states strong non-speculate, weak no-speculate, weak speculate, and strong speculate. And I'm going to increment a saturating counter that will move it towards strong speculate. So the idea is that I'm going to learn to speculate this load, and when I know that this load is safe, I'm going to be always speculating it. So I'm going to have an entry in my load buffer, and my entry will contain the memory address of the operand where I'm loading from. There will be a speculation bit that will tell me whether this load is being executed speculatively, and there will be an update bit. The update bit is a bit that indicates if I should update the predictor at the commit or abort times, and this update bit is set by the stores. So each load instruction has a load spec bit that will indicate if it should speculate according to the predictor. So the way it's going to work is that at the load decode stage, I'm going to set the load spec bit based on the value of the predictor. So I did the decoder of the load. I have the instruction address of the load. I'm going to use the instruction address of the load to hash into the predictor table. And that table will contain a value, contain a predictor, right? Either speculate or do not speculate. I'm going to use the value of that prediction to set the load spec bit that I'm going to use in the load table. So after the load operand address is computed, then I'm going to ask, are there any uncommitted younger stores? If there are no uncommitted young store, I do not need to speculate this load. The spec bit will be 0 because I can simply proceed with this load, and the update bit is always 0. And I'm going to issue my access to the cache because I know that there will be no conflict because there are no uncommitted younger stores. If there are uncommitted young stores, then I'm going to look at the load spec bit that was set according to the predictor. And if the load spec bit is 1, it means that I must speculate this load. So I'm going to enter this load into the load buffer, and I'm going to set the speculation bit to 1, saying this is a speculative load. If the load speculation bit is off, then I'm going to enter into the load buffer the tagged opcode and saying this is not a speculation, but I'm not going to access the issue to the cache. This load is going to wait. So this is like the pessimistic solution. So there is no speculation here because I am waiting until the stores are resolved because the load spec bit told me that I should not be speculating. At the start commit stage, I'm going to do an associative search in the load buffer. And for all matches in the load buffer, I'm going to look at the spec bit of that entry, and I'll see whether the load have speculate or not. So if the bit is off, it means that that load did not speculate. So I can set now the update bit to 1. because that load should have speculated. So that load should not have speculated. So it was corrected to not speculate. And I should keep not speculating. So the update bit equal 1 causes the predictor to move to a strong no speculate state. If the entry spec bit was 1, then I'm going to abort the load because notice that when I have a match, the store is matching a load that's in the load buffer. That is when a conflict happens. So in that case, if I have that load and the load was speculating, and that is indicated by the spec bit equal 1, then I must abort that load. And then I will move that predictor to a strong non-speculate state because I should not speculate this load in the future because I want to avoid future conflicts. And then of course, I have to recover from the misspeculated state. At the load commit stage, so a load is committing now. So I check whether the spec bit is on. So was this a speculative load? If this is a speculative load and I'm committing, it means that it was okay to speculate. So I'm now going to increment the saturating counter. Speculation was correct. If the spec bit was off, then I'm going to check the update bit. If the update bit is also off, then I'm going to also increment the saturating counter because I would like to speculate in the future. If the update bit is on, then I'm going to move the predictor to the strong non-speculate state. So this is what we had for this lecture. Let me just close the meeting here.